All right, everyone, welcome back to Grad Student Seminar. Today we have Roberto talking about infinite dimensional calculus.
So, hi everyone. I will try to look at the chat, but if you have a question, I would suggest you to just unmute yourselves and ask the question. So, well, thanks for the organizer first. And okay, so today I want to talk about infinite dimensional calculus, but I will actually start talking about PDEs because the real motivation for studying infinite dimensional calculus, aside for being maybe interesting on its own to see how things that you learn in undergrad generalize to more more dimensions, let's say, it's also that you can actually apply that stuff to real world problems and find something interesting. So let's say that we have a differential equation. Like, I will stick to this example for the entire talk, the entire talk, because it's, well, because it's nice. So let's say that we have this equation, Laplacian of u plus e to the lambda u minus 1 equals to 0, where u is in x, some space of functions. We will see later what are the requirements on x, but I don't want to say anything else that what I will say later about what the structure of these x must be. But if you want to be a bit more concrete, you can think of x like the space of C2 alpha functions, like functions with two derivatives plus a bit more on Rn. But it's not really important here. The important thing would be just what the structure of this x is as a space. And lambda is some parameter in R. And now we can ask some questions. The first question is there any obvious solution? And the answer is yes. If you take u equals to 1, okay, obvious is not really a mathematical term, but if you take u equals to 1, that's a solution. You just get 0 plus e to the 0 minus 1, which is 0 for every lambda. And the second question might be, okay, we know that there is this solution. Are there values of lambda for which this is not the only solution? So we lack uniqueness. So this is a priori a hard question because this equation is nonlinear. The nonlinearity is very bad because we have e to the lambda u. It's not super bad because the nonlinearity is not in the differential part, but just in the non-differentiated part. But anyway, it's nonlinear, so a priori these kind of equations are hard to study because the tools that we have for linear equations apparently don't apply in this situation. So what we can do is to think of this equation as the zero set of some functional. So we have a functional from x cross r to y, where x is our space of functions and y is another space of function. And we are kind of quite free to choose what these functions, these spaces are. And this functional takes, u lambda and sends it to Laplacian of u plus e to the lambda u minus 1. And we are looking at the zero set of that. So we can try to quote unquote graph this linear functional in the Rx plane as some curve. And we already know that u equals to 0 is a solution for our lambdas. So for sure, the R-axis is there. But maybe there are other solutions, like other branches that do something like this. And maybe they cross our trivial solution or not. So of course, if I take a point here, if I choose this lambda, then I have more than one solution. So for this lambda, I don't have uniqueness because I have the trivial solution plus this solution plus this solution. So we want to spot these points for which we don't have uniqueness. And something we can do is this. Okay, maybe finding branches that are far away from the trivial branch is hard, but maybe we can look at what's happening near our trivial branch and see if there is some criteria looking at lambda at our trivial branch and at f to spot other solutions nearby that one. So if we look at points where these two branches crosses, what's happening is that near those points, we have two branches that are coming out. And so for points, for values of lambda near these points, we have two different solutions or more than one solution. Because we have these two branches that are the same at that lambda, but they are different for lambdas that are close by, but not equal to our lambda. And that might remind you of something you learn in calculus, which is the implicit function theorem. It tells you when you can spot, when you can write the zero set of a function as the graph of the other variable in a parameter. So the goal now is to develop this theory of the theory that leads to the implicit function theorem in this more general setting of spaces of functions, which are spaces a priori of infinite dimension, and see what we can get out of there to see if we can like spot these points where two branches cross, and so points where for nearby values of lambda we have non-units. Okay, so this is the introduction, and then I go to the starting point, the original idea of the starting point of this talk. So, any question up to now? Is it clear what I want to do? Okay. Okay, so, well, when we are in undergrad, we learn that we can study functions, so study the geometry of function, the shape of the function of functions in R and then in Rn, looking at things like derivatives and looking at when the derivative is zero, so we get maximum, minima, or when the derivative is not zero, and we get things like the mean value theorem or the implicit function theorem that tells us the implicit function theorem or the local inversion theorem are like a way to relate the geometry of the function with the fact that we can the functional property of the function, so we can locally invert the function in a neighborhood. So what we want to do now is to generalize these theorems, and to do that we need to first choose what spaces we're talking about, and two, we'll need to define derivatives. So first, the spaces. Okay, so the definition that probably most of you, if not all of you, have seen is the one of Banac space. So a Banac space is a couple, is a couple x comma norm of x, where x is a possibly infinite dimensional vector space over some field k. And we will just take k equal to r, because that's the natural setting for when we study PDEs. Well, maybe it's C, but let's take r. And this is a complete norm. That means that it's a norm for which all Cauchy sequences converge. So that's the natural setting of this theory. So it's basically a vector space where we have a norm that behaves nicely. And the vector space can be infinite dimensional, but we'll see that that's not an issue. So let's say that now we have a function from a Banac space to another Banac space. We have no hypothesis on this function a priori. To this function, we can associate a norm, even if, well, we still don't know what the space of function is, so we can not really call it a norm, but we can associate a number, which is defined as the supremum over all x's in x of the norm of f of y of f of x in y over the norm of x in x. And then we can look at the space of linear functionals from x to y. So A is linear, and we also ask that the norm is bounded. Then we can look at this object with the operator norm. Oh yes, this is called operator norm. So when we look at this object with this norm, this is a Banac space as well. And this will be important later. So just as a notation, if the norm is finite, we say that F is continuous or bounded. And I will use these two terms interchangeably. So please be patient with that. I've been thinking about this for a while, and they are the same for me now. So I will not notice if I say one thing or another. So this is the setting. This is all we need to know for a moment about these spaces. So now, as I said, we need to define the notion of derivative. So maybe you remember from calculus that in Rn, you have two notions of derivative. One is called the Thresher derivative, and one is the Cateau derivative. That they are different. One is stronger, is the Thresher derivative. And there is some way of defining them. And in this setting, the way we define derivatives is exactly the same. So the first thing we define is the Thresher derivative. So we say that f from x to y is Thresher differentiable or just differentiable at a point u in x if we have a linear operator a from x to y such that the residue, which is this function, it's the increment of f from u minus the increment of a from u, the small o of the norm of h. I'm going to say what that means for every h in x, where that means that the y norm of this residue over the x norm of h goes to 0 as the x norm of h goes to 0. So you can like locally approximate the displacement in f by the displacement with a. And if f is differentiable at u, then this a is uniquely determined, and it's called the Thresher differential, and it's denoted by df at u.
Is the middle term supposed to be f of u instead of f of u?
Yes, sorry. Thank you.
Thanks.
Right, thank you. Okay, so if f is differentiable in the entire x, then to f we can associate a new map which takes points in x to continuous linear operators, which is just taking u to the differential of f at u. And if this map is continuous, we say that f is C1. And okay, so there are some rules for this differential, which are the ones that you want. Sorry. And that they're ones that are true in Rn as well. So D is linear in F and satisfies the chain rule. This is actually coming from the definition. You just need to do a computation. It's easy and not going through that. But it's important to say that because this differential behaves in the way you want. And as I said, this is not the only definition of derivative. You also have a weaker definition of derivative, which mimics the one that you have in R. So in R, when you define derivative, you define the derivative as a limit of the increment ratio. So you can try to do the same thing here, and you actually get a notion of derivative, which is though weaker than this notion. And this notion is called Cateau derivative. So f is Cateau differentiable at u if we have a linear operator a from x to y such that this operator is the limit of the increment ratio. So f of u plus epsilon h minus f of u over epsilon, where epsilon is just a number now, goes to ah for epsilon going to 0 for every h in x. So now the point is that the increment ratio can be computed in different directions, and you're asking that for every direction you get the same operator. And the fact that you can compute the increment ratio in different directions is actually the thing that breaks these two definitions in two different objects, the Thresher differential and the Gateau differential. And its effect, well, it's actually just looking at the definition, that Thresher differentiability implies Gateau differentiability. But the converse is false, and there is actually more. Gateau differentiability does not even imply continuity. And the example is the same. Well, we already have a counterexample in R2. So if you take f of s and t, defined to be s squared t over s fourth plus t squared for t not 0 and 0 for t 0. This is not continuous, but it's Gateau differentiable. And maybe you have seen this example in.
Can I ask a quick question here? When you have a nonlinear function, f is bounded and continuous still the same, like it is for linear functionals?
I'm calling them bounded and continuous. I mean, for me, bounded is being finite. Yes, there. So if this norm is finite, when you have a sequence x and going to x, that means that the norm of xn minus x goes to 0. Then you automatically have f of xn minus f of x.
Okay. So then the being Thresher differentiable does imply continuity, I guess.
No, that's not true. Sorry, that's my bad. That's not true because you don't have linearity. Sorry.
Okay.
No, they are not the same notion. Yeah. Thank you. Thank you.
Okay.
Yeah, I've not been thinking about this thing for a while, so sorry about that. Yeah, they're not the same notion, but okay. We call bounded this fact, and continuous the same thing. So maybe I should write just bounded here. Thank you for pointing that out. Okay, so just to give you an example of how to compute these derivatives, we take our functional, Laplacian of u plus e to the u minus 1. Just take lambda to be 1. Then when we compute the differential of this, well, okay, so what is the fu? This is a linear operator, so we need to apply that to some element h in x. So the way you compute this derivative, so I can already tell you that this is Thresher differentiable. And so you can actually compute it using the increment ratio, because it is also Gateau differentiable. And the two differentials, of course, coincide by uniqueness. So what you do is just you take derivatives, treating u as a variable, as a normal variable as if it was in R. And I mean, this is the quick, dirty way of saying that. So, and you treat linear operators as linear operators. So lambda, Laplacian is linear. So when you take the derivative of Laplacian of u, you can just swap it with taking the differential operator of u and then taking Laplacian. So you get Laplacian of h plus the derivative of e to the u is just e to the u, and then you need to apply it to h. So it's very, it's more or less what you expect, and it's very concrete. Okay, so the first theorem that we see that generalizes is the mean value theorem. So So we have f from x to y g differentiable, Gattoni differentiable for every u in x. And then we have this statement f of u minus f of v in norm of y is bounded by the supremum along the segment UV. Segment is just the curve parameterized by gamma t equals to tu plus 1 minus tv of the Gattoni differential of f. This is in the Lxy norm times u minus v x norm. Sorry, I lost one. Okay, here. So why? And the idea here is that you want to. This is actually an idea that comes very often in this infinite dimensional setting. Is that you can often reduce your situation to a finite dimensional one. And so the idea here is to reduce to dimension one and apply the standard mean value theorem in dimension one. So we can take f of u not f equal to f of v, otherwise we have nothing to prove. And we can take also psi in the dual of y, which is just, sorry, psi in the dual of y, which is linear functions from y to r, such that the norm of psi in y star is 1. And when we apply psi to f of u minus f of v, this is the norm of f of u minus the norm of f of v. This is a non-trivial fact that's coming from Banac's theorem, which is a fundamental theorem in functional analysis. So there is some work to be done here, but it's actually a fundamental fact. And we can also define this function, which is the way we go down to one dimension. So we take this function h from 0, 1 to r, defined to be as h of t is psi applied to the image of this segment using the parameter t. So now we can compute the derivative of this h. Sorry. So what's the increment ratio? This is bilinearity of psi. This is psi applied to, okay, there is some small computation to be done here, but you can check that this is f psi applied to f of gamma t plus tau minus 1 plus tau times 1 minus v minus f of gamma t over tau. Now, if you call this, that was the h of the previous definition, and this was the u of the previous definition. By the fact that u is Gattoni differentiable, for t going to 0, this goes to gamma of the Gattoni differential of f at gamma t. Sorry, psi of the Gattoni differential of f at gamma t. So this is h prime of t. And now we apply the standard mean value theorem to h. So the mean value theorem applied to h says that h1 minus h0 is equal to h prime of theta for some theta in 0, 1. And in particular, this is less than the sup of h prime in 0 for theta in 0, 1. But what we have on the left side is this gamma of f of u minus f of v. So on this side, we have the difference, the norm of the difference, y. And on this side, we can bound it by the norm of c times the norm of the differential times, where is it? Sorry. Yes, I forgot u minus v here. times the norm of u minus v. So this is less than the norm of c times the sup over the segment of the norm of the Threshold differential times the norm of u minus v. This is 1, and this is what we wanted to prove. So again, the main idea is that we reduce to dimension 1, and there we can apply the standard theorems that we know in finite dimension, and then we go back to infinite dimension. So a corollary of this is that if f is Cateau differential, and we also know that dgf is continuous, then f is Thresher differential. And of course, the Thresher differential and the Cateau differential coincide. And this comes from applying the mean value theorem to this increment, to this residue here with A equals to the Cateau differential. But anyways, so from now on, we will just think about Thresher differentiability, because aside for pathological cases, they are actually the same. All good? Okay. So higher derivatives. So the way you define higher derivatives is the thing you expect. You take the derivative of the differential. So the way you define the n derivative of f at u, this is just the differential of the n minus 1 differential of u. But the thing I want to say here is this. So let's look at, okay, the first differential is a map from x to the linear operators from x to y. The second differential will be then a map from x to the linear operators from x to the linear operators from x to y. But there is a nicer way of looking at that. This is canonically identified with bilinear maps from x cross x to y. So if you keep doing that, the nth differential would be a map from x to the n linear maps from x to y, x cross x and times to y. And so for instance, still our example, f of u is Laplacian of u plus e to the u minus 1. df of u, again, we need to apply it to some element h. This is Laplacian h plus u e to the u h. And now if you take a second derivative of that, now we need to apply it to h and k. So when we take the derivative, we're taking the derivative in u. And sorry, sometimes my touchpad gets crazy and does weird stuff. Okay. When we take the derivative in u, the first piece here doesn't have any u, so the derivative of that, when we differentiate in u, is just 0. Sorry, there is no u here. And when we take the derivative of this second piece, we get e to the u, and then we add an h, but now we need to apply it to k. Now we take the third derivative at h, k, l, we will get e to the u, h, k, l, and so on. So that's the way you could do that. And there is something you can see here. You can see that if you swap h and k, it doesn't change anything. And this is actually not a coincidence. That's actually a theorem, which is not hard, but a bit technical. And the theorem says that the evaluation map that takes n elements of x and sends them to the n f of u evaluated at, sorry, that's not the evaluation map. No, yes, that's the evaluation. Well, whatever. This map is not just bilinear, it's actually symmetric. again, here the assumption is that we have Threshold differentiability up to 1. Okay, so that's all I wanted to say about higher derivatives. There is one more thing, which is partial derivatives. And the way you define partial derivatives is the way you expect. You fix all the variables but one, and you take the derivative in that variable. So going back to our full functional f of lambda u, that was the plus n of u plus e to the lambda u minus 1. The partial derivative in u, I'll denote it with putting a small u at the bottom of f. This is, again, we need to evaluate that on h. This is the Laplacian of h plus lambda e to the lambda u h, while the derivative in lambda u applied to mu will be, there is no lambda in the first entry, so that is 0. And the second entry is u e to the lambda u applied to mu. And if you take the derivative, and you can keep doing that, you can take the derivative u of that or the derivative u of that and keep doing that and get higher order partial derivatives. And as in Rn, we have the theorem of Schwartz that says that we can swap the partial derivatives. So we can first compute the lambda and then compute the u, or we can first compute the u and then compute the lambda, and we get the same result. Okay, so now finally to the, if there is no question, to the local inversion theorem and implicit function theorem. So everyone's good? Okay, so local inversion theorem and implicit function theorem. Okay, so first we might define this set. We call invertibles from x to y the set of A, which are linear from x to y, and that are invertible in Lxy. So it means that there is an element of Lxy, a linear bounded functional that composes on both sides to the identity either of x or y. And so the first thing we can say about this is that from the closed graph theorem, A injective and surjective implies that A is invertible. This is the fact that we have linear operators is important here. And one might say, okay, what do we know about this set? Because for a moment it's just a set. And the first thing we know is that this set is open in the space of linear unbounded functionals. There is a more precise statement of that, which says that, so if A is invertible and T is linear, and the distance from T and A is less than 1 over the norm of A to the minus 1, then T is invertible. And the second fact is that the map that takes an invertible element to its inverse is C infinity. This is a nice thing to know. It's useful in the proof of local inversion theorem when we look at the regularity of the inversions. But well, we won't really use it, but I think it's nice to know. Okay. So the local inversion theorem says that, okay, so let F be CK. Okay, higher regularity is defined in the way you expect. So it's the continuity of the K differential. So let's say that F is a CK functional from X to Y with K at least 1. And we know that the differential of F at some point U star is invertible. Then F is locally invertible in the sense that there is a neighborhood of U star and a neighborhood of the image of U star where F is invertible with CK inverse. And to prove that the inverse has the same regularity, you actually use this fact that the inversion operator is C infinity. I will briefly sketch the idea. It's very sketchy, and I won't say much. So if it's completely not understandable, don't worry. It's not important. But I think it's nice to say what the idea is, because it shows you something else about how you do stuff in this setting. So, well, okay, we can assume U star is 0 and also F of U star is 0. That's just a change of coordinates, quote unquote. And we can also assume that F is the identity of X plus psi. And to do that, we compose with the inverse of the differential. This is invertible by hypothesis, so we can compose with that and we get something like this, where psi is C1 from X to Y, and the differential of psi at 0 is 0. Whatever, you can do that. So the mean value theorem shows that, implies that this psi is a contraction. That means that the norm of psi of U minus psi of V is in Y is less than the norm of U minus V in Y, in X, sorry. And now we look instead at this other function, phi V of U. We define it as V minus psi of U. Of course, this is a contraction as well, because psi is a contraction. But this maps PR to BR itself when the norm of V is less than R over 2. You can check that. It's just a small computation. And now, by Banac fixed point theorem, we have a unique fixed point of this phi V of U. So there exists a unique U such that U is equal to phi V of U. Phi V of U is V minus psi of U. So that means that F of U is V. So U solves F equals to V. So it inverts. And this is local because we need V to be contained in a small wall. Quote unquote, end of the proof. And I wanted to say that because it shows you something about how you do stuff here. One thing is you reduce to finite dimension. The other thing that's a very common idea in analysis is that if you want to prove the existence of a solution of some equation, a good way to try to do that is looking at, to try to use some fixed point theorems. So fixed point theorems basically tell you there is a solution of a certain specific kind of equation. So maybe if you can put your differential equation in that form, you can use some fixed point theorem and see that there is a solution. Okay. Somehow a consequence of this theorem is the implicit function theorem, which is the one we are really interested in for the purpose of what I was saying at the beginning of the talk. So I will not prove this theorem because there is too much work. It's technical and it's not that too interesting in this setting, I think. So T, X, and Y are Banac spaces, and F is CK from T cross X to Y, with K at least 1. So somehow you can think of T as the parameter. I mean, there is a certain degree of freedom in choosing this parameter. In our case, the parameter was in R, but here T can actually be a Banac space. So suppose that, we know a root of this f, which is lambda star u star. And we also know that the partial derivative in u, lambda star u star, this is a linear operator from x to y. And assume that we know that this is invertible. Then what the theorem says is that there is a neighborhood lambda of lambda star, and there is a neighborhood u of u star, and there is also a function g, which is ck, so the same regularity as our function from lambda to x, such that in lambda cross u, we have that f of lambda u is 0, if and only if u is the graph of lambda through this function. So that means that, well, this is the zero set of our functional. If we find a point where the partial derivative, so this is in tx, if we find a point where the partial derivative in u is invertible, then we can find a neighborhood where the zero set can actually be written as the graph of some function in the variable t. And this is kind of getting there to what we want, because this is at least telling us which points are not giving us non-uniqueness. So for those points in a local neighborhood of the curve of zeros, we have that there is no other branch, kind of, because it's a graph of a function, and so there cannot be any other branch, because that would not be the graph of a function. So the application is the thing I was saying at the very beginning. And actually, the theory is bigger. This is the starting point of the so-called bifurcation theory. This bifurcation theory is interesting because, or at least it was interesting to me because it can be applied to PDEs, and it's probably through something more general. Probably you can do more, but I don't know that. So let's go back to our equation. We had Laplacian of u plus e to the lambda u minus 1 equals to 0. So we had our trivial branch. Sorry, we had our obvious solution, u equals to 0. And I will call it trivial solution because it's always 0. Now, what is the implicit function theorem telling us? We can look, so as I said, we can look at this equation as the zero set of f of lambda u equals to this functional. So we can now try to apply the implicit function theorem to this f of lambda u. So the implicit function theorem tells us that if along this branch u equals to 0, we have only points where the differential of f in u is invertible, we cannot have branches that are coming out from our trivial solution. So things like that cannot happen if for every lambda the differential of f along u at lambda 0 is invertible. So points where two branches are from which a non-trivial branch is coming out are called bifurcation points. So these points here are called bifurcation points. And that's why the theory is called bifurcation theory. And something that we already know from the implicit function theorem is that I'm basically reversing what I said before. So a necessary condition for lambda to to be a bifurcation point. A bifurcation point of f from u equals to 0 is that, well, the implicit function theorem must fail, and really the only way it can fail is that this condition is not true. So we need that f of u of lambda star 0 is not invertible. So if you have the f of u is invertible, we cannot have a bifurcation point because locally we have the graph of a function, so there is no other branch coming out. And the thing is, okay, if we only had that, we wouldn't know much. But this fact is true in the converse, in the sense that the fact that f is not invertible implies that lambda is a bifurcation point if we add some extra hypothesis. And this is the first theorem of bifurcation theory. That's called the bifurcation from the simple eigenvalue. So theorem, bifurcation from the simple eigenvalue. So, okay. The first extra hypothesis is that f is twice differentiable from R cross X to Y. And so f satisfies that f of lambda 0 is 0 for every lambda. And we let lambda star to be such that now we need three hypotheses. The first is that f of u is not invertible, so the kernel, well, first hypothesis is that the kernel of f of u is not zero, but there is more. We ask that the kernel is one-dimensional and it's spanned by this element u, by some element u star in X. The second thing we need is that the image of f of u, lambda 0, is codimension 1 and it's closed. So these things together imply that f of u is Fredon of index 1, sorry, of index 0. Well, that's whatever. And the third condition is like a non-degeneracy condition. And the condition is that the derivative in u and lambda star 0, computed along u star 1, is not in the image. Sorry. I don't know okay, sorry. Is not in the image f of u lambda star 0. And this is the way I think of this condition is more or less like, you know, when you want to compute, so if you have a function from R to R and you want to find the maximum and minimum, you take the derivative and you set the derivative equal to 0. And then if you want to know if the derivative is, if you have a maximum or minimum, you compute the second derivative. But if the second derivative is 0, you still don't know if it is a maximum or minimum. So you need somehow non-degeneracy condition. And it's also like a condition reminiscent of the non-degeneracy in Morse theory that Mohammed was talking about last week. And actually, bifurcation theory uses a lot of Morse theory to do more advanced stuff. I mean, this theorem often fails because you cannot do things explicitly, so maybe, but you can get more advanced theorems using Morse theory, but that's too much for this talk. But anyways, I still have to say what the consequence of this theorem is that, as you expect, lambda star is a bifurcation point. And there is more. Moreover, the set of non-trivial zeros near this bifurcation point is given by a unique C1 curve. And you can actually tell what's the shape of this curve near the bifurcation point. What I mean is that you can tell if something like this is happening, where the bifurcating branch is developing for values of lambda that are smaller, or something like this is happening, or something like this is happening. And the way you do that is really explicit in the sense that you compute a number. And by computing a number, you can differentiate between these three cases. Computations are really explicit. So going back to our original example.
Sorry, could I ask a question about the theorem first? In my mind, like X and Y are Banac spaces, so they're infinite dimensional.
Yeah.
So what do you mean by condition 2 that the image has codimension 1? I was just a little confused there.
It means that, did you say, sorry, okay. What does it mean? Well, these are vector spaces. You can try to think of them as like, you can take the quotient of Y with this image, and that's dimension 1. So that's, and if you have an inner product, you can say that your orthogonal is dimension.
Okay, that makes sense. Thank you.
Yes, thank you for asking. But okay, so the picture in your mind should be, okay, if you have an inner product, you're saying that the orthogonal is dimension 1. In general, you don't, but you can take the quotient of Y with this image, which is a vector space, because fu is linear, and that is dimension 1. So going back to our example. So we want to know if we have non-trivial solutions. So if you have solutions that are not u equals to 0 for a certain value of lambda. So we are hunting for points where something like this is happening, or maybe something like this is happening. So we are hunting for bifurcation points. Because nearby, once more, that's the thing I said at the beginning, so maybe it's better to say that again. If we find one of those points and we take values of lambda that are close by, we get that for those lambdas, we have two different solutions. So we can say that uniqueness is, that there is no uniqueness. And so that means that there is a solution which is not u equals to 0. So these are f of lambda u. So you look at the derivative at lambda 0 of f along u, you get, sorry, of course, okay, we need to apply that to h. And you get the equation lambda Laplacian of h plus lambda e to the lambda u, but u is 0. So this is just e to the 0 times h. So that's the equation lambda h plus, sorry, Laplacian of h plus lambda h. And the fact that we have kernel which is spanned by a unique element u star means that we're looking if we're trying to see if this equation has as a solution a one-dimensional space, a one-dimensional subspace of X. So, and if we find this one-dimensional subspace up to like checking the other conditions, but that's more work to be done. It's doable. If you find that this equation has a one-dimensional subspace as a solution, then you can, so if this equation has some non-trivial solution that is not h equal to 0, you can apply the bifurcation from the simple eigenvalue theorem and find that your original equation, which is nonlinear, has a neighbor of lambda for which you don't have uniqueness of solution. So the fact that you have a non-trivial solution for your original equation boils down to checking if you have a non-trivial solution for the linearized equation. And that's why this thing is useful, because looking at solutions of nonlinear equations is stupidly hard, but if you look at solution of linear equation, that's manageable. And so the entire thing I want to say is that you can reduce the study of nonlinear equation, at least some properties of nonlinear equation, to the study of the same properties of the linearization, to changing a bit your parameter. And the fact that you have a parameter is actually not that important, because you can, most of the times you can like force your problem to have a parameter, which is like a dummy parameter, and then you get rid of that. Somehow you do some like cut and paste and things like that. And the second thing I want to say, the fact that the trivial solution is u equals to 0 is not really important, because if you have some other branch like this and you want to, so if you know that you have this solution u star, you want to see, or maybe call it u bar, and you want to see if you have any other solution spawning out from there, you just like change variables so that your functional is 0 along is. So what I want to say is that this u bar is sent to 0, and so you change your function. But the important thing here is that you need to know that there is a solution. You need to know that there is some branch, because otherwise you cannot apply the implicit function theorem. So the implicit function theorem doesn't hold if you're not along a solution branch. Well, okay, I think that's all I wanted to say. So thank you. I hope it made sense.
Okay, thank you so much for the wonderful talk. Are there any questions for Roberto?
Yeah, could I ask still another question?
Sure.
Can you say anything about the set of the bifurcation points? Is it always like smaller dimensional or something? Can you make sense of that? Or can you have, like in your R example, can it be dense?
Okay, so in my calculation, I get this to be 91.
So I'm not sure I understand your question. What can be dense?
Like, is the set of all bifurcation points of...
Oh, the set of bifurcation points. I don't know. That's the honest answer. Okay, I think it really depends a lot on... No, okay, it does. Depend a lot on your choice of spaces x and y. Because you see, if you change x, you can get very different things. So for instance, if you look at this equation and you're looking at functions h that are also L2, you don't get anything. You get just h equal to 0 because of the maximum principle. But if you choose your space in a different way, maybe you get, for some values of lambda, you get lambda equal to 0. But you get that there is a non-trivial solution of that. I don't know if these bifurcation points can be dense. I don't know, but I feel that this fact that this regularity condition here might force you to, at least in this very simple case, might force you to not have accumulation. But honestly, I don't know. So
okay, thank you.
Roberto,
yeah,
I have a question. So if I look at complex Banac spaces, and then the notion of differentiability is holomorphy, right? That is, if something is special differentiable, then I can call this holomorphic. And then in in this setting, do we know if Gaussian differentiability implies Thresher differentiability?
I think the answer is no, because so this differentiation you have here is not
because in finite dimensions it is the case, isn't it?
It's not taking a derivative of a function. It's taking a derivative of a function between two. So I mean, I don't know how would you make sense of a functional between two Banac spaces over C being holomorphic? I don't know. When I was thinking about these things, my word was just R. So I've never thought about that. But I think that these two concepts are sufficiently different, like the concept of derivative of functions Cn and this differentiation of functionals between two Banac spaces. That, I mean, this differentiation is not a standard derivative in the sense that it's not that you're taking the derivative of the functions. So if X is a space of functions, you're not taking the derivative of the function in X. You're taking the derivative of the map sending these functions to some other function.
Yeah.
So maybe you can make a notion of holomorphicity for functionals between Banac spaces over C, but honestly, I don't know. But it feels like they are not really related. Right?
All right. Thanks.
Okay. Any other question? Okay. Well, then thank you for listening.
All right. So thank you very much, guys. I think the next talk is going to be in 2 weeks, so it's going to be a break, Thanksgiving. So enjoy this 1 week of holiday. I'll see you guys in 2 weeks then.
Break. Thanksgiving.
Yeah.
Great talk, Roberto. Thank you.
So it gave you a kind of summation. So it said,
All right.